Just a reminder that the next homework assignment is due on Monday already. It's covering Chapter 9 here. So we'll finish up Chapter 9 probably pretty quickly here today. And I think you guys should be all set for doing those homework 8 problems. And then we'll have one more homework assignment based on Chapter 12 and 13 that'll be due probably the following Wednesday, following Monday, something like that. Questions or comments before we get started? No? Okay. Well, we're going to wrap up our discussion here on Chapter 9, talking about doing inference, confidence intervals, hypothesis tests on 2 samples. So far we've talked about doing the t-test, or I guess we also talked about the z-test there for 2 populations when we're looking at the population mean, the difference in means. And we're going to finish up Chapter 9, not surprisingly here, with kind of that other case that we looked at in Chapter 7 and 8 when we're looking at a population proportion. So before we were looking at the difference in population means, now we want to do the same types of things for the difference in proportions from our 2 populations. So we want to estimate P1 minus P2, where P1 is a certain proportion of something from one population and P2 is a proportion of the same thing from a different population. So kind of going back to our usual thing all along here is we want to figure out what an estimate for that parameter is. So if we want to estimate P1 minus P2, how can we estimate that? And so we want to find a good estimator and then kind of figure out the properties that we need about that estimator. So what is its standard deviation or variance? So if we have, not surprisingly, like we did before, if we want to estimate the population means, we use the sample mean. If we want to estimate the population proportion, we'll use the sample proportion. So if we have P1 hat and P2 hat from 2 samples that we have, so P1 hat comes from a binomial with M observations with probability of success P1, and Y comes from a different binomial with N trials and probability of success P2, then and they're independent, then we'll have our estimate will be unbiased. So if we take the difference in proportions, it'll be unbiased, and its variance will be that thing there. So let's quick work out how that, make sure that's true. So we have x and y are independent. That's important. X is distributed as binomial, and P1 and Y is distributed as also binomial, N trials P2. And we're looking at P hat 1, so our sample proportion from the first population, from the first sample, and the sample proportion from the second sample there. Okay, so then we want to just confirm that we have an unbiased estimate here of what we're trying to estimate, and then kind of derive what its variance is. So the expected value of P hat 1 minus P hat 2. Well, again, we can distribute it's going back to our properties of expectation here. We can distribute the expectation through the subtraction there. So P hat 1 again is x over m, and P hat 2 is y over n. Again, we can pull that constant outside, so this is 1 over m times the expected value of x minus 1 over n times the expected value of y. So what's the expected value of x? We have binomials here. Yes. So the expected value of a binomial is number of trials times the success probability. So that's m times P1. Similar for expected value of y, n times P2, which does indeed give us what we want. So this is P1 minus P2. Okay, so we do indeed have an unbiased estimator here of that difference in proportions that we're trying to estimate. So we can use the sample proportions, and that'll be an unbiased estimator. Okay, and then let's quick write down how we can figure out the variance of this estimator. So the variance of p hat 1 minus p hat 2. Well, that's the variance of x over m minus y over n. Okay, and again, if we use the fact that x and y are independent, we can distribute that variance through. We can just take the sum of each of those variances because they're independent. So this is the variance of x over n. We have the negative 1 that's squared, so that goes away. It's the variance of y over n. Sorry, that's an x over m. This is by independence. Same kind of thing we've been doing all along here. Okay, so then we can pull that denominator, square it, and pull it outside. And then what's the variance of a binomial? Do you guys remember that? Harkening way back. So binomial NP has variance what? Yep. All right. So the variance of binomial is n times p times 1 minus p. So if you just match up the right sample sizes there, this will be the variance of x is m times p1 times 1 minus p1 over m squared. That m squared comes out because that's in the denominator there. Plus n times p2 times 1 minus p2 over n squared. And then ran out of space here, but some n's and m's will cancel from the numerator there, and that'll give us the variance that was on that previous slide. Okay, so this is kind of the usual strategy here for doing inference on whatever parameter you're interested in. Is find an estimator of that thing. Maybe you want something that's unbiased. Maybe you want to use one of the other criterion that we used. And then figure out what its properties are. So what is its expected value and what is its variance? And then you can kind of use that to figure out how to derive your test. So hopefully you're kind of feeling that process going here. So again, we want to estimate this difference in proportions. So we have our estimator for that, the difference in sample proportions. And so again, we need to know then the distribution of what our estimator is, and we're going to fall back on some results that we've seen before as well. So by this normal approximation, as long as our sample sizes are large enough in some sense, we've seen this before. So the same kind of thing that we saw back in chapter 7 and 8 when we were doing inference on proportions. And then we can use the fact that a linear combination of normal random variables is also normal. That's a chapter 5 thing. And so again, as long as our sample sizes are large enough, this fact will be true. So this difference in proportions will also approximately follow a normal distribution with mean here. This is the expected value of p hat 1 minus p hat 2, and this is the variance. Okay, so that's approximately the distribution of our estimator there, as long as our sample sizes are large enough. So the binomial approximation for each sample proportion comes from the same thing that we've seen before, and then because a linear combination or some sum or some addition or subtraction of normal random variables also gives you a normal random variable. This is the result that we have here. Okay, so we can use this fact to construct tests and confidence intervals just like we have done before. So let's kind of get our get all the details straight for here for what we're going to do. So when we're testing a difference in proportions, first we'll talk about a test, then we'll show the confidence interval. Our parameter of interest again is P1 minus P2. That's difference in proportions from each population. Our hypotheses are going to be exactly the same, probably exactly what you would expect. So our null hypothesis will be that there is no difference, and then the alternative will be that the difference is either not equal to 0, greater than, or less than. So depending on what the question of interest is here. And maybe I'll just make a quick note that if you remember back to the two sample means test that we were doing, our null hypothesis was that mu1 minus mu2 was equal to some delta 0. And then that was usually going to be 0, but it could have been something else. So but for this case, we will be putting a 0 in there. So we'll only be sort of the underlying theory only holds here. That underlying distributional approximation only holds if we're saying that difference is 0. So when we're doing proportions, we'll always be testing: is there no difference, or is there some other difference that we're interested in there over in the alternative? So just to note that we'll only be testing 0 there in the null hypothesis here. So again, of course, next we want to observe our independent random samples from each population. So again, what we have here is we'll have x1, x2, all the way up to m will be IID Bernoulli with success probability P1. Okay, so each one of our observations will be a 1 or a 0 based on yes, it is a success for whatever we're looking at, or 0, it's not a success. And then we'll also have a sample of y's here, y1, y2, all the way up to yn, which will be IID Bernoulli, but with a different success probability there. And these will be independent. These will all be independent of each other. Okay, and so then maybe just to make this connection, if I define an x without a subscript to be equal to the sum of all these xi's up to m, that thing is going to have a binomial distribution with m trials and probability of success P1. Similarly, a y without a subscript, the sum of all my y's is going to be binomial NP2. So I don't know if this is something we've talked about before, but there is this connection here between the Bernoulli and the binomial, that if you add up a bunch of binomial random variable, if you add up a bunch of Bernoulli random variables, you'll get a binomial random variable, which I think sort of makes sense. Bernoulli, we're looking at each individual thing as a success or a failure. Binomial, we're looking at a total of n objects. How many of those are successes and how many are failures? That's a result that we can use. Okay, so then we have our data. Now we want to perform the testing procedures, and here's what our test statistic will be here in this case. So what's not written here is that we're subtracting off a 0, right? So it still kind of has the same form. We're taking our estimate minus the null, the hypothesized value, and we're dividing by the standard deviation. Okay, so we still have the same form. Again, because we have normal distributions, we're not looking at a t or anything. We're going to use a z. So we have p at 1 minus p at 2. That's our estimate. We're subtracting off the hypothesized value for the difference in proportions, which is 0. And then we're dividing by kind of a messy looking thing, where p hat here is listed at the bottom. Okay, so it's not quite the variance that we calculated before for our difference in proportions. So why do we use this p hat without a subscript? Does anybody have an intuition for why we would do it this way? So p hat is like an overall successes out of total number of observations. So we have x successes from our first population, y successes from our second, and we divide by the total sample size m plus n. Does anybody have an intuition on why we do that for our test statistic? Yeah.
Well, since with the null hypothesis, you're assuming the proportions would be equal, then the total proportion of the combined should be the same.
Yes, exactly right. So the comment was, remember, the null hypothesis says that P1 minus P2 is 0, or P1 equals P2. Be an equivalent way of saying that. And so if those sample proportions, if those population proportions are the same, then it's sort of like you have one big sample. So it's sort of like you can put those two populations together, and it's just like you have one population. So we can calculate an overall sample proportion here. The null hypothesis tells us that those populations are essentially the same. So we have we can put all of our successes over our total observations together. So this is the sample proportion, or the overall sample proportion, assuming that P1 equals P2, and we have sort of just one population from that, that we're looking at total number of successes out of total number of observations there. Okay, very, very good. So then our caveat here, remember we said this, or are there any questions or comments you guys can think of on why this is our test statistic? Is that okay? So again, it has that same form, but now when we're looking at this example, if our population, if the proportions are really the same, then we sort of have we can sort of make this slight adjustment here. Okay, so remember our distributional assumption held as long as our sample sizes were large enough. So we're going to go back to the same criterion that we were looking at before when we dealt with proportions. But now we have two samples, right? So we need both of our sample sizes to be large enough. So our test statistic will have that standard normal distribution as long as those four checks are true. So as long as m times p1 hat and m times 1 minus p1 hat are at least 10, same for the second sample. So that will be our check here for proportions, just making sure that we have our independent random samples, and also that those four quantities are all bigger than, or at least 10. Okay? And then finally we'll, again, after we've calculated our test statistic, we'll make our conclusion. So we'll calculate p-values, and then reject. We'll compare the p-value to alpha. Then we either reject or fail to reject. And we'll do both of these things in the exact same way as we did with the z-test before. So we'll calculate p-values in the exact same way that we did that before when we had a z-test statistic. Okay, so again, nothing new happening here as far as the conclusions go. Okay, so that's how we'll do a test. Figure out how we can do a confidence interval. Now this formula will look a little more similar to what we to that standard deviation calculation that we did. So if I want a 100 times 1 minus alpha % confidence interval for the difference, again I'll take my same structure here. I'll take my estimate plus or minus a critical value times the estimated standard deviation. So I have my estimate is that difference in sample proportions plus or minus a z critical value. So we'll go back to the z there. And then, again, the variance of our estimate depended on P1 and P2, so we can plug in our estimates here and get something that we can actually calculate again. And again, this is also sort of useful or appropriate to use as long as your sample sizes are large enough. So same checks that we did for the test that we'll do here. Okay, so kind of moving through these a little more quickly now. I think you guys are getting the hang of it. Let's do an example here to finish up the chapter. Okay, so here we're going to look at loyalty here. So you can imagine yourself working for a bank or something. The question you might have is someone who switches brands, or so this could be any context, because of a financial inducement less likely to remain loyal than someone who switches without inducement. So I think I got one just in the mail yesterday, a little card from Huntington Bank. If I get a checking account there, I'll get $200 or something like that. Do you guys get those as well? Yeah. So that's what we're talking about here. So if you switch to Huntington Bank because they gave you an incentive, are you more or less likely to stay loyal than someone else who switched without that incentive? Okay, so we'll let P1 and P2 denote the true proportion of people who switch to a certain brand with and without inducement, and who then make a repeat purchase, so are somehow loyal in some sense here. Okay, so first let's do a hypothesis test. So we want to test this difference that the proportions are the same versus that the difference is less than 0. So again, P1 is the proportion that was those who switched with the inducement. And then we have the proportion loyal without the inducement. And so is that the alternative hypothesis that you would want to test? Does that make sense? Do I want to, or why does a less than 0 make sense there? Because P1 would be smaller, right? So your intuition might tell you, or what this if you worked for this company, they might assume that possibly people who do switch with inducement are less likely to be loyal. So you'd want to see if that difference is less than 0 here. And I think that's kind of what this first question says. Are people who switch because of the incentive less likely to be loyal? So that's kind of why we have a less than 0 in there. Okay, so you can imagine we collected some data. So we had 200 people who switched with the inducement and 600 who switched without, and we had those number of successes there. 30 from the first group, 180 from the second group. So let's let X be our sample from the first group. So that's a binomial with 200 trials, success probability P1, and we'll use P hat 1, which is 30 over 200, or 0.15. Okay, and similarly we have Y is binomial with 600 trials, success probability P2, and P hat 2 is the 180 over 600, which is 0.3. Okay, and while we're at it here, let's calculate our P hat, which is sort of our overall proportion here. That's 30 plus 180 over 200 plus 600. Which is 0.2625. Okay, so just kind of calculating some things there before we jump into this. Okay, so sort of our criteria for being able to use this testing procedure is we need independent variables, so we need x and y to be independent, and we need our sample sizes to be large enough. So we need independent samples, and we need large enough. Okay, so we're not told that x and y are independent, but well, we're not told that x and y are independent, so we need to assume this. So we need to assume that we have independent samples, which probably makes sense. We'll trust that this company has done a good job collecting data. And as far as large enough goes, m times p hat 1, that's our number of successes, that's 30. M times 1 minus p hat 1, that was our 170. We have n times p hat 2, which was 200, or sorry, 180, and we had n times 1 minus p hat 2, that was 420. So these are all greater than or equal to 10, so we're okay with our large enough condition. So if we assume that our samples are independent here, they're large enough, so we're good to go there, and we can sort of proceed with our test here. Okay, so let's proceed with the test. We can do our test statistic here is p hat 1 minus p hat 2 minus 0 divided by the square root of p hat times 1 minus p hat times 1 over m plus 1 over n. Okay. And so up top we have 0.15 minus 0.3. The denominator we have big square root here, 0.2625 times 1 minus 0.2625 times 1 over 200 plus 1 over 600. All that's under the square root. And if you work that out, you'll get negative 4.18. Our test statistic is really, really big on the negative side. So our test statistic is negative 4.18. Okay, so next, what do I want to do after I calculate my test statistic? Everybody said p-value, exactly right, or at least one person said. Okay, so this is the probability that a standard normal, and then we'll compare that to 4.18. And what's the inequality that goes in there? Less than. Why is that? Yep. So look at my alternative as a less than, so I put a less than in there. And if you guys have looked at the normal table long enough, what's that probability going to be approximately equal to? One more time. Yeah, this will be approximately 0. So something very, very small. Okay, so then I didn't. Oh, I guess I did tell you use alpha. Alpha was 0.01 here. So what is our conclusion? We will reject the null hypothesis because our p-value is very small and less than alpha there. Okay, so because the p-value is less than alpha, we will reject the null hypothesis. So that is their, well, would anybody like to try to interpret that for me? So we reject the null hypothesis, so what does that mean? Try saying that in our formal language here.
There is sufficient evidence to conclude that proportion loyal with inducements is less than proportion without inducements.
Exactly right, yes. So again, there is evidence that the alternative is true, which states that the proportion who switch with inducement are less likely to be loyal than those who switch without inducement. And if you're ever sort of wondering how to interpret that, how to interpret a alternative, you can kind of go back to your question of interest. So the question originally asked, is someone who switches brands because of inducement less likely to remain loyal than someone who switches without inducement? Well, yes, we found evidence for that. So you can just say there is evidence that, and then start in right there. There is evidence to conclude that someone who switches brands because of blah blah blah. So you can look back to your question of interest to kind of think about how to interpret these things. So let's write this down. There is sufficient evidence to conclude that someone who switches brands because of inducement is less likely to remain loyal than someone who switches without. Okay, so again, there is sufficient evidence to conclude that someone who switches brands because of inducement is less likely to remain loyal than someone who switches without inducement. So it should be no surprise there. It's always good when the result of a test sort of gives you the intuition that you would expect. That means probably doing something right here. Okay, questions or comments on this? Is that all right? Okay, so kind of maybe I haven't done this quite in this way, but sort of the usefulness of then doing a confidence interval for this difference is, okay, so we said that there is a difference. We said that P1 minus P2 is less than 0, but we haven't said what that difference is, right? So if we calculate a confidence interval, that will tell us how much less likely is someone who switched because of inducement going to remain loyal. So we can use a confidence interval for this. So again, we already checked our conditions. So we can kind of just jump right into our calculations. So again, we want P hat 1 minus P hat 2 plus or minus Z alpha over 2 times P hat 1 times 1 minus P hat 1 over M plus P hat 2 times 1 minus P hat 2 over N. And we can start plugging numbers in here. 0.15 minus 0.3 plus or minus a Z alpha over 2 times a big standard deviation. So this is 0.15 times 0.85 over 200 plus 0.3 times 0.7 over 600. So imagine that's there under the square root. And then if I want a 90% confidence interval, what's my Z alpha over 2? $1.64. It sounds good. Yep, 1.64. I think we might even put a 5 in there, but 1.64 would be fine as well. This is because we want a 90% confidence interval. And if you do all those calculations, you will get negative 0.2017 all the way up to negative 0.0983. Okay, and I'm talking about proportions here, so is it okay that I have negative numbers in my confidence interval? Yeah, right. We're talking about a difference here, so it's totally fine for us to have negative numbers in here. Yeah, you wouldn't want anything outside plus or minus 1. That would be a bad sign. Okay, so let's interpret this thing. So what we can say is we are 90% confident. We're 90% confident that. And actually, let's anybody out there want to give this one a try? Interpret this. Nobody wants to try it? You guys are very quiet today. Come on, somebody. Do this one for me. Anybody?
We're 90% confident that proportion the difference people who switch financial incentives.
Mm-hmm. Yeah, so we're talking about the difference here. So we're 90% confident that the difference between people who switch with and without inducement is somewhere in this range. We can say that a little more clearly. I mean, that's a fine interpretation. But again, the proportion that switch with inducement, since this interval is negative, the proportion that switch with inducement is somewhere between that range, much less than the group that switched without. So I'm 90% confident that the proportion, let's say, of people who switched or of switchers who are loyal is between, and say what our interval is here, so is between about 9.8% and about 20.2%. We'll say it's higher for the group that did not switch because of inducement. So higher for those with without inducement. Switchers who are loyal is between higher for okay. So we're 90% confident that the proportion of people who switch to this brand who are loyal is between about 10% and 20% higher for those who switched without inducement. So we said those proportions are different, and here's our estimate for how much different they are, somewhere between 10 and 20%. Okay, so yeah, there are different ways that you could interpret this, which would probably be equally fine. This is one way to interpret that interval. Okay, I think that wraps up Chapter 9. Any closing questions or comments you guys have on this two sample stuff? No? Okay. Well, then let's move on to Chapter 12. Kind of bringing us into our final major topic of this course. Chapter 12 and 13 we'll be talking about the same thing. This is titled Simple Linear Regression. Anybody heard of regression before? Yeah. So again, kind of like the confidence intervals and the hypothesis tests, I guarantee that you will see regression later in your career. So again, this is something that you will definitely see. Okay, so what is regression? Well, so up until this point, Chapter 7, 8, 9, we were talking about we did inference on one variable, right? So we were either talking about a single population, we were looking at a single variable, or even if we were looking at two populations, we were looking at the same variable from each of those populations. And so in regression analysis, the goal is to start looking at relationship between two variables. So whereas before we were assuming we had independent samples or something like that, here we're going to kind of exploit the dependence that often exists between variables and try to say something about that relationship between two variables. So we'll have bivariate data again now. So we have samples of two variables from each of our n individuals. So, for example, from you guys, I could collect how tall you are and what your GPA is, or something like that. I could collect pairs of variables on each of my individuals, and then I want to figure out what's the relationship between those two variables, and specifically, we want to figure out how to model a linear relationship between these two variables. Okay, so a few definitions before we jump in here. So again, we have these two variables that we're going to look at, and we'll give each of these names. So we'll call one of them the explanatory variable. We'll call the other one the response variable. And if you've seen this before, you've maybe heard the explanatory variable called the independent variable, and the response variable called the dependent variable. Have you guys heard that before? Independent, yeah. So we're going to go with explanatory and response because by now we have sort of a very different sense of what the word independent means, and so I don't want to confuse that. So that refers to the same thing, but we'll go with explanatory and response. So sort of by definition, our explanatory is what we fix, the experimenter fixes, or kind of something that we can observe. And then the response is the variable that we're sort of not controlling, but that depends on this explanatory variable. So we'll call x our explanatory variable, and we'll call y our response variable. And again, kind of keep in mind that dependent, independent, dependent terminology refers to the response variable sort of depends on the explanatory variable here. Okay, so just kind of to quickly think about for pairs of variables what the explanatory and response variable are. I think in these two examples it's fairly straightforward, but in other cases it's not always so straightforward. So if the two variables I'm looking at are high school GPA and college GPA, what would you use as the explanatory variable, and what would you use as the response? So which one of these is sort of influencing the other one?
High school influencing.
Yes. Thank you, Craig. Yeah, so the high school GPA will be our explanatory variable. And the college GPA will be our response variable. So you could think in general the college GPA might depend in some way upon your high school GPA. What that relationship is, we're not saying yet, but it certainly can't go the other way, right? Your high school GPA can't depend on what your college GPA is. There's a time component going on there. So you could imagine that the college GPA is somehow being influenced by the high school GPA. How about this second example? If we're looking at the weight of the car versus its fuel efficiency, this one's maybe a little bit more straightforward. What's our explanatory and response? So which variable is sort of influencing the other one? Yes. So the weight, certainly the fuel efficiency is not influencing the weight of the car. It'd be the other way around. So the weight of the car will be again our explanatory variable, and the fuel efficiency would be our response. Okay. So again, we're looking at these two variables, and we'll give them our explanatory and response names here, and then kind of use what we think the relationship might be to kind of formalize that into a statistical framework here. Okay, so again, just to emphasize this point again, when we're talking about regression, we're looking at a linear relationship between our variables. And so if we want to model the relationship as a linear relationship, then we need to make sure that that's appropriate. So we want to make sure that relationship between those variables is actually linear before we try to model it that way. And so we can kind of make this determination in a simple case by looking at a scatter plot here. And I think I've shown you some scatter plots before, but again, a scatter plot will just put our explanatory variable on the x-axis, and we'll put our response on the y, and then we'll just plot the various combination of points there. So we'll put its x value on the x-axis and its y value on the y. Okay, so when we're looking at these scatter plots, there's sort of four things you should consider when you're looking at a scatter plot. We have the direction, the form, the strength, and are there any unusual features? And so by direction, again, we're looking for a linear relationship. So is it a positive relationship or a negative relationship? Okay, we want to think about what the form of the relationship is, and so here we'll simply go, is the form, does it look like a linear relationship or a nonlinear relationship? Okay. Strength will go just kind of how strong is the relationship? Is it strong or is it weak or is it somewhere in between? And then unusual features, we want to kind of note if there are there any outliers floating around in our data set. So if we have two variables, if we have observations on two variables from our n individuals, we can use a scatter plot to look at the data to kind of get an initial idea of what the relationship between those two variables are. We can think about it in terms of these four things. Okay, so let's look at an example. This is, again, I think this is out of your textbook. We're looking at the efficiency ratio for a steel specimen immersed in a phosphating tank. So we have our first variable is the weight divided by the loss, and then we also have temperature on data on the tank temperature. So we're looking at the temperature versus the efficiency ratio, and there in your notes I've given you a scatter plot of the data, and again, using that scatter plot, we can sort of describe the relationship between these two variables. So what's the relationship between tank temperature and the efficiency ratio? Okay, so we can sort of do this sort of more of an exploratory terms here. So here's our scatter plot. On the x-axis, we have the temperature of the tank, and our y-axis, we have the efficiency ratio there. Okay, and if we want to describe the relationship here, again, we'll sort of do it in terms of these four things. So the direction, is there a positive or negative relationship between these things? So, yeah, is there a positive or negative relationship here? Positive, right. So larger temperatures correspond to larger efficiency ratios, and the opposite is true as well. So we have a positive relationship. That's pretty straightforward. What about the form of this thing? Do you think that's a linear relationship or a nonlinear relationship? So you think it's not linear? It's kind of linear. Enough for statistics. That is actually what I was going to say. It's maybe not a perfectly linear relationship, but you're probably never going to see a perfect linear relationship in here. So kind of thinking about, you sort of have this type of a thing going on in general. Look at the general relationship here. So it's at least somewhat linear. Okay. What is the strength of this relationship? Is that weak? Is it strong? Yeah. I would say this is it's maybe it's moderate to maybe sort of weak. It's not overly strong there, just by looking at it anyway. And then are there any unusual features that you would be concerned about with this data set just by looking at the scatter plot? Yeah. So if you erase my lines, there's maybe some weird things going on here. Again, they're not too crazy. It's not like you have a point floating around up there or something like that. So yeah, so there's maybe some strange data points, but I would say there's nothing too crazy about this scatter plot. So there's nothing too concerning here as far as our outliers go. Okay, so if you're again just using a scatter plot to summarize the relationship, is it positive or negative, linear versus nonlinear, and then is it weak, is it strong, and then maybe just pointing out if there's any weird observations going on in your data set. Okay, so a scatter plot, we can sort of qualitatively talk about the relationship. To sort of quantitatively talk about this or give a numerical summary for this relationship, we're going to go back to this idea of correlation, which we saw back in Chapter 5. And again, it's something I'm sure you've all heard of before. So just remember that the correlation kind of measures the strength of this relationship. So, but make sure we point out it measures the strength of the linear relationship between two variables. And so what we'll use for this to calculate from our data is we'll use the sample correlation coefficient, which we're going to call R, and that will be this formula right here. And I will never ask you to calculate that by hand. we'll let technology do that for us. But just that is the formula that we have here. So it's again, that's a numerical value for telling us the strength of the linear relationship between two variables. Okay, and so just some properties of correlation. Correlation doesn't matter the correlation will be the same regardless of which variable you put in as your x and as your y. So regardless of which variable is the explanatory or response, your correlation is going to be the same. And again, if you look at the formula, you can imagine if you switched x and y in there, that's not going to change. The formula is going to stay the same, right? So it doesn't matter which is your explanatory, which is your response, the correlation is the same. The value of R doesn't depend on the units in which x and y are measured. So whatever the units are, we have sort of a standardized way of measuring the relationship between them. So whatever the original units are, correlation doesn't have any units, and you can kind of see that here. You have the units on top, and you're dividing by units as well. So you can see that the units sort of cancel out of this formula. The correlation will be between positive and negative 1, and the strength of the linear association gets stronger as R moves closer to plus or minus 1. So if you get all the way out to exactly 1, that means you have a perfect linear relationship. And as you get closer to 0, that relationship gets weaker. Okay, so just throw some pictures up here, some sample correlations here. Kind of going from something that's very strong in a positive way, so it's very, very closely centered around a line there. Moderate, it kind of gets less condensed around a certain point there. There's a plot maybe in the upper right of there being no correlation between those two variables, and then you're kind of going in the other direction. You have moderate negative and then strong negative. And this is just a good time to point out that well, if the correlation is 0, that doesn't mean there is no relationship between the variables, right? The correlation of 0 means that there's no linear relationship between the data. So in that lower right pattern here, there is sort of a very strong curved trend there, right? But if you took the correlation of those numbers, it might be something that's very close to 0, saying that there's no relationship. So just keep in mind that correlation is talking about a linear relationship. So just because the correlation is small doesn't mean there is no relationship. It just means there's no linear relationship between those variables. Okay, and just to finish things up here, just to note that correlation is very sensitive to outliers. So that's kind of one reason we're looking at a scatter plot to see if there are any outliers. If you have anything crazy going on there, that can really influence your correlation. And so thinking about our weak, moderate, strong correlation, sort of our rule of thumb here is that weak is if R is between plus and minus 0.5. So somewhere less than 0.5 usually means there's a very weak relationship. If it's between negative 0.8 and negative 0.5, or 0.5 and 0.8. That's sort of a moderate relationship, we could say. And a strong is anything bigger than 0.8 or less than negative 0.8. So if R is less than negative 0.8, R is bigger than 0.8. But again, this is sort of very specific to the application. I know in the sciences, if you're doing some sort of a test between relationships, you need that correlation to be like 0.99 or something like that. Where in the social sciences, correlation of 0.4 to 0.6 is sort of more acceptable for establishing a relationship there. Okay, so just real quick, if we calculated the correlation from that scatter plot we had up there a minute ago, we see that the correlation is actually pretty high. So linear relationship there is 0.6. The strength of that is 0.6719. So we might say that's a moderate relationship. And so if there is a linear relationship, then we can kind of proceed with modeling that linear relationship, which is what we'll get into next time. So sorry I kept you over a minute. Thank you guys for being here, and have a good rest of your day.